Hey, hi friends. Today in this slide, I'm going to speak about how you do visualize a dynamic programming. So potentially you have top-down approach. You have a memory allocation. You have a optimal substructure. You have a space complexity. You have a recursive call. You have a bottom-up. You have a base case. You have a dynamic programming table, and you have an overlapping subproblems. So when you hear about these keywords, you need to connect these dots, and the question that falls around these will be primarily around the dynamic programming. Okay, so what is the universal engine of a dynamic programming? So every DP problem is solved by breaking into a state, defining the transition, and caching the result. So where I am, how do I move, how have I been here before? So basically, you define cache state, then it's equal to your transition states. So without memory, recursion recalculates the sum problem infinitely, resulting in exponential OT on time complexity. So this is of brute force recursion. So you have a 6 ways to do it, then you have a 3 way, then you have a three, and then it goes all. But if you bring the memory, your recursion just goes into ON, which is kind of a linear growth. And so in a hash map, you go for only 3 ways, ways three. Now let's see um, what is the difference between a memorization and tabulation? Basically, it's memorization is a top down, tabulation is a bottom up, and then there are dimensions around this, which is called like the execution directions. So in a memorization approach, you start at the goal, recursively ask for prerequisite, whereas in a tabulation, you start at the base case, loops iteratively up to the goal. Memory structure is a hash map for call stack. Here you have tabulation, you have an array and a table. Stack overflow risk is high because you are doing a deep recursion tree. In tabulation, it's no because you are doing an iterative loop. Best use case is when do you use a memorization when the sequence of subproblem is unclear. When you use tabulation when there is a clear predictable sequence, example grid reversal, and for memorization it's like a partition problem. Now, let's say there is a one pattern which is like a constant transition. The state depends on a fixed number of previous states. Example, minimum cost of climbing stair, which can be represented by dpi is equal to cost I plus minimum of dpi minus 1 comma dpi minus 2. So it's a 0 1 memory window. An optimization inside it is that it's an A1 array is unnecessary. Keep only the variable required for the immediate transition. Pattern 2. The two-dimensional grid. Movement is strictly limited to downward or rightward paths. Example, unique path dpij is equal to dpi minus 1 j plus dpi j minus 1. So you see a base class 111. Then in the pictorial you can see these are representations. So in order to reach to dpij, I need to go from dpij to and then I add dpij minus 1, I reach here. So space optimization stores only a single row to achieve ON space. The pattern 2, it is a two sequence mapping, comparing two strings by building a dynamic coordinated system. Example, longest common subsequences, base cases is STONETOWER. So if SI is equal to TJ, then it's called diagonal plus 1. If SI is not equal to TJ, max is equal to topless. Pattern 4, interval expansion. The result for a larger interval depends strictly on the smaller interval nested inside it. Example, longest palindromic subsequence, interval expansion, TOTAL, interval expansion. Inner evaluated bounds, evaluated outer bound, SI and SJ, match. Example, T is equal to T, take interval plus 2. Mismatch, T is not equal to L, max of sinking left or sinking right. The interval dynamic programming transfer quick. Outer bounds depends on inner bound. Matrices must be populated by interval length, not row by row. Step n, full string, final answer. Step 2, length 2. Step 1, length 1, base case. Pattern 5, non-constant transition. The current state must scan all previous states to find the optimal path. Example, longest increasing subsequence 3152. Target node. Time complexity spikes to ON because fixed loop hacks are impossible. The algorithm must check every element j where j is less than I. Pattern 6. Next picks target sum. The DP array index represents the target sum itself. Example, partition equals subset sum. Crucial detail. Swap right to left to prevent reusing the same element twice. A left to right swap updates value that will be erroneously used again in the same direction. Base case. Sum 0 is always true. target capacity. The universal engine across dimensions, regardless of the problem saved, the underlying mechanics never changes. 1D linear loop back, look back, I minus 2, I minus 1 and 1. Simple linear dependency on fixed preceding states. 2D coordinate look back, state depends on neighbors in a grid or a matrix. Interval inside out look back, I minus 1, J plus 1. Expand, building solutions from smaller subintervals to larger one. Next spec, capacity look back, state transition based on remaining source or capacity. So state plus transition plus memory is equal to optimal substructure. The master DP pattern cheat sheet, pattern name, constant transition, identifying saying fixed, previous steps, 1D array plus 2 variables, time space ON or O1, 2D grid, XY movement constraint, 2D matrix or 1 row, time space is OM into N and ON, 2 sequence, comparing 2 strings, 2D matrix or 2 rows, OM into N / ON, interval, DP, single sequence, nested bounds, 2D matrix, diagonal fill, ON square ON, non-constant, scanning all prior states, 1D array, ON square ON, next spec target, finding specific sum, 1D array index is equal to sum, ON sum by O sum. Okay, thank you.